spent a lot of my time there working on Avalanche Go, and the networking code is some of my favorites, so I thought I'd give a presentation about that. First, I want to say thanks to all the people that made it possible for me to be here, including all of my coworkers at Avalabs. Second, I got off an international flight this morning, so I'm kind of jet lagged. So apologies for any errors or omissions. I'll try to keep the energy level up. And yeah, I'll pause periodically for questions, and then I'll take some time at the end as well. I thought that I was going to be able to just mirror my laptop screen, and I was going to like go into my IDE and show you guys a bunch of code, but apparently I'm just going to have the slides, which don't have as many code snippets as I would have liked, but I can just try to describe things to you in great detail, and you can go look for yourself afterwards. Okay, so here's kind of an agenda of what I'll talk about here. So the first thing is how do nodes identify each other? What does the network topology look like? How do nodes find each other and connect to each other? What do you do once you are connected to someone? And what are you actually sending? And then finally, we'll cover some security concerns and how we try to mitigate those. So every node in the Avalanche network, whether you're a validator or not, has a node ID. And this is just a hash of a certificate. This is just an ordinary X509 certificate. There's nothing special about it. You could generate it by just doing like OpenSSL rec, blah, 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 right? So nothing special or mysterious there. Okay, so this node ID is 20 bytes. And, well, I think I covered everything on this slide. So I'll come to this later, but during the TLS handshake, you use the key part of the key certificate pair to prove that you are who you say you are. This is how you connect like the on-chain identity of like node ID such and such with like when I'm actually talking to you, how do I know that that is you? Okay, so I've included a snippet of the function where we convert a certificate to a node ID, which has its own type in Avalanche Go. Whoops. Okay, so there's a bunch of different network topologies that you could have in distributed systems. So for example, you could have one where everybody is just connected to the person that is left or right of them, which is a ring. You could have a star, which is kind of a hub and spoke model where all the messages first go through some kind of like central hub. And Avalanche is a mesh network. So every validator is connected to every node in the network. That is not true of non-validators. Non-validators do not connect to other non-validators, right? So everybody needs to be connected to validators because as part of consensus, you'll send queries to validators, and in order to send them queries, you need to be connected to them. So far, so okay? I'll pause there if there's any questions.
Did you say Avalanche is a mesh network?
Yes.
Connected to all the nodes?
Yeah, all the validators are connected to everybody, whether they're a validator or a non-validator, and non-validators do not connect to non-validators. Okay, this is all the stuff I just said. Okay, so how do peers actually find each other, right? Because when you start this program, Avalanche Go, you're not connected to anybody. And eventually you need to get connected to all of the validators. Or if you're a validator, you need to get connected to everybody. So how do you actually find each other, right? So ignoring the question of how do you get to be connected to the first set of peers that you're connected to, which I'll come to in a second, when you're connecting to another node, you exchange a subset of your peer list as a gossip mechanism to spread information about who is in the network, right? This is how we disseminate information about who all is on Avalanche right now. Okay, so let's say that like I connect to some other node, we're doing our handshake, which I'll also talk about in a second, and I say, hey, by the way, here's some nodes that I'm connected to. I just randomly sample them. And if you hear about some node that you're not connected to, but you want to be, then you will start up a new thread trying to connect to the IP address that was given to you by the person that you just did the handshake with. Okay, so like with all gossip protocols, there's a trade-off here between how chatty you want the network to be and how fast you disseminate information, right? So if I give you like a huge peer list, I give you like 500 peers during this handshake, then that's going to be a lot of bytes sent over the network, but you'll get connected to everybody really fast. And then the opposite is true as well, right? If I give you a really small peer list, then you're not going to connect as fast. So in addition to this, nodes periodically just gossip a subset of peers to each other. So it's not just on the handshake. So during the handshake, you always exchange a subset of your peer list, and then occasionally you'll just fire off some subsets of your peers to everybody. Well, not to everybody, to a subset of the people that you're connected to, so everybody can stay up to date on who's in the network. Okay, so yeah, we have a question here.
Is there a minimum number of minimum number of peers that should be shared across all nodes in the network?
So eventually, all the validators should be connected to everybody. There's no requirement in terms of just like a hard number of peers that you should be connected to, but you have to be connected to at least some portion of the network's stake in order to be able to make progress during consensus, right? So if I'm only connected to like 50% of the stake of the network, then I'm not going to be able to reach consensus on the blocks that I'm processing, because I won't be able to issue queries to the nodes that I want to, right? So as part of Avalanche consensus, I do a bunch of like random subsamples of the validator set weighted by stake, right? So if I try to sample node A and I'm not connected to them, then that query is going to fail, and it's going to be harder for me to make progress towards consensus. So I need to be above some minimum percentage of stake connected in order to make progress. It's not like a constant number of nodes that you need to be connected to. Does that answer your question?
Yes, thank you. And is there a way that I get to choose what kind of node do I send a query to?
Not really. You send queries to validators based on the percentage of the network's stake that they represent. So if node ID A has 1% of the network stake, then you have a 1 in 100 chance of sampling them when you do a random subsample as part of the consensus mechanism. And a lot of this networking stuff is really deeply tied to Avalanche consensus, but if I included like everything related to Avalanche consensus, it would be like an hour-long talk and not a half-hour one. So I'm gonna kind of omit some of the consensus details. But if you have questions, then I would be happy to elaborate on things if something doesn't make sense. Okay, so before I was talking about exchanging peer lists with each other, and there is a message type in Avalanche Go called peer list, right? So there's a place in the code that I wanted to show you where we enumerate all of the kinds of messages that could be sent back and forth between two nodes, and one of them is called peer list. And a peer list is a bunch of these guys, right? So each of these structs here represent a node on the network that someone is sharing with you, or you are sharing with them, right? So let's kind of look into this as an example. So the first thing is they share the node's certificate, right? So this is just another way, essentially, of sharing their node ID, right? Because you just hash this twice and you know the node ID, right? So if you have this information, you can figure out, do I want to connect to this node ID, right? Because let's say that I get one of these and I hash it twice and it says you got node ID A, right? And node ID A is a validator. So I'm like, ooh, I do want to connect to this person if I'm not already. So the second field here is the IP address and port that you can reach the node at, right? So if I'm sharing this peer list information with you, it's not super useful for you unless I tell you like where to find them, right? I can't just say, here's their ID, good luck, right? You need to like actually know what address to dial to. And then you also have a timestamp and a signature. So this is a little interesting. So let's say that like I tell you, you know, there's this node ID A, right, that I gossip to you, and someone else also tells you that there's a node ID A. And those two messages, let's say, have, those two node IDs are the same, but let's say that the IP addresses are different, right? Like I tell you that you can find node ID A at 1.2.3.4, and someone else is like, you can find them at 5, 6, 7, 8, right? Like which of those should you actually try to dial, because they can only be at one of them. So what we do is we include a timestamp and a signature of their certificate over the IP and time. So let me say that again. You include their signature, the signature of the certificate over the IP and time, so that you can verify that, that this is the freshest time, and that it actually, the freshest time and IP, I should say, and that it actually came from that node. So when I'm sharing my information with you, I include what I think my like clock time is and my IP address, and then I sign it. So now you can give that information to other people, right? And if they see something signed by me and I say my address is 1234 at time 0, let's say, and they see another thing from me that says my IP address is 5678 and the time is 1, both of those messages are signed by me, so they know it's really from me and not someone else, and they can say, well, the one with the later timestamp is probably the better guess for what your IP is, because I've changed my opinion of what my IP address is. Does that make sense? I know that's a little hard to follow. Okay, seeing nods, good sign. Okay, and there's a bunch of other message types that I wanted to kind of poke through, and we'll talk about some of them in a bit. Okay, so every node on startup starts a go routine where you're just constantly listening for inbound connections, right? So we have this process in place that we've talked about for like for disseminating information about who's in the network, and this is the part where we actually like accept the inbound connections, right? Other people are hearing about my my IP and who I am and that I exist and that I'm online, and now they're trying to dial me. So we have this go routine, which I can't pull up here, unfortunately, but it's just basically a for loop that goes on for as long as the node is alive, and it says accept connection, and then try to do handshake. Accept connection, try to do handshake, and on and on and on, right? Because you just want to keep accepting inbound connections and establishing new connections to peers as long as Avalanche Go is running. And then similarly, every time I hear about someone and I want to connect to them, I start a go routine that's like, try to connect to this node, try to connect to this node, right? So let's say that you gossip to me 2 node IDs and I want to be connected to them. So I'll start a go routine that basically says, as long as I want to be connected to this node and I'm not, just keep dialing them. And there's a back off, of course, so that you're not just like spinning trying to dial this node. And then a couple different things could make that go routine exit, right? The first is you succeed in connecting to them. Nice, the happy path, right? So like I'm trying to connect to node ID A, I dial them, they accept the connection, we do the handshake, we're connected, everything is happy. Another thing that could happen is that I find out about a newer IP address for node ID A, right? And this is the situation that I was talking about before. Someone gossips to me one of those structs that I showed you before, and the IP address is different than the last one I saw, and the timestamp is later than the previous latest one that I saw, right? So I'm trying to dial 1234 with timestamp 0, and now I hear that your IP address has changed to 5678 with timestamp 1, so I'm like, okay, well, I'm going to go with the timestamp 1 IP address and stop dialing on the 1234 address. Okay? Questions? Yes?
Is the handshake?
Oh, I think they were going to hand you the mic so that they could hear you online.
Hello. Okay. Is the handshake using TCP?
I am about to answer that on the next slide. Good question.
Thank you.
Any other questions? Okay, yes, very, very good question. So there's kind of like two handshakes going on here. There's a handshake within a handshake. So we use TLS to prevent man-in-the-middle attacks, right? So like if node A and node B are talking, how do you make sure that there's not someone in between that's secretly intercepting your messages and changing them and passing them along and pretending that they're you, right? So node ID A thinks that they're talking to node ID B, but actually there's someone in the middle, and when node ID A sends some chits, maybe the interceptor changes them before passing them to node ID B, right? We don't want this. So we use TLS to get around this, and this is pretty common pattern across all web services. And this is how, again, we connect on-chain node IDs to actual like peers that we're connected to, right? So on the platform chain, we keep track of the validator set, right? We say like node ID such and such is a validator, node ID such and such is a validator, and so on, right? And we need to know which peers that we're connected to, right? Like actual like TLS connections. We need to know which TLS connection corresponds to which person on chain so that we can send them messages, right? So in Avalanche consensus, for example, let's say that node ID A has 1% of the network stake. I happen to sample them as part of Avalanche consensus, and now I need to send them a message, right? And I need to make sure it's actually going to that node and not some other node. And this is how we establish that you are who you say you are, right? So we do this TLS handshake, and we use the staking key and certificate in that handshake so that like you can't complete the handshake unless you actually have the key corresponding to the certificate that you advertise. Okay, so the TLDR is that you do a TLS handshake, and by hashing the certificate in the handshake, you know who you're talking to. So far, so okay? Question?
What protections are there against the cycling of the snake?
All right, I'm going to ask you to repeat it with the mic. Sorry.
I was wondering what protections you have against the reuse of stake. I've noticed that, like, if I have a validator that expires, it continues receiving gossip. So obviously, like, other validators on the network are still treating me as if I'm a validator, even though my stake has expired. So is there like conditions under which you'll perform the handshake again, like to stop someone from, say, like letting all their stake expire and creating more validators? So you're sort of like, pretending that you have a lot of validators using the same stake.
I mean, in theory, you should just immediately stop receiving queries, and people should immediately stop treating you as a validator if your validator end time has been reached. So let's say like at time T, you stop being a validator. Like everybody should immediately stop sending you queries like at time T, and then thereon you should never receive any queries. And I think what you're saying is that you've observed that that's actually not the case.
Yeah, I continue receiving gossip after expiry. So I was wondering, like, maybe there are some conditions by which you'll like recheck to prevent people from like gaming it in that manner.
I'm not sure why that would be, but I would be interested to find out the answer.
Okay.
Okay, so the other part of the handshake is what I'm going to call like the Avalanche handshake, and this is a two-part thing. So as soon as you establish a connection to someone, you do this TLS handshake, right? Now you know who you're talking to, what their node ID is. And then the first thing that you send them is what's called a version message. And again, I was going to link to the actual code here, but I can't. So here's some of the things that are in the version message. You include what your network ID is. You give your clock time. You give what you think that your own IP address is. And you provide that signature over what you think your clock time is and your IP address so that that information can get passed around. So remember a few slides ago when I was like, you include in the peer gossip message, you include the time, the IP address, and the signature. Well, this is how everybody finds out about your IP address, time, and signature. It's because you tell them during the handshake. Okay, so then when you receive a peer's version message, you do a bunch of checks, right? You make sure, like, are they on the right network ID, right? Because, like, for example, mainnet has some network ID, and then the Fuji testnet has some other network ID, right? So if someone is, like, lost, so to speak, right? Some Fuji testnet node is trying to connect to a mainnet node. This is where they both realize, like, we shouldn't continue to connect. Like, we're not part of the same network. This is a different thing. You also make sure that your clock is in sync with theirs, right? So if you connect to someone and they're like, I think it's time t plus 100 minutes or something, and you think it's time t, then you're like, okay, well, something's kind of wrong here, so I'm just not going to connect to you. And there's a few other checks that we do here. Okay, so you both send each other a version message and do like your sanity checks on your respective parts. And then you send each other one of these peerless messages. So you say like, hi, nice to meet you. Here's my version and some stuff. Okay, everything looks fine. And then you send them a peerless message to say, hey, by the way, here's some nodes that I'm connected to. Maybe you want to connect to them too. Okay, and then once you have received the peer's version message and validate it and everything looks okay, and then you receive their peerless message and that all goes fine, only then would you even consider processing different messages, different message types, right? So if you haven't sent me your version message and then you immediately start sending me any other kind of message, like you send me a query or you send me a block or whatever, I'm just going to ignore it until you finish the handshake. Okay, pause for questions. Cool, I'll take that as a sign that I'm doing a good job. Okay, so for each connection that you have to another node, there is an instance of this peer struct, and it does like what you might kind of expect it to do, right? So from the peer struct, you're running a few different Go routines. One of them is read messages, right? So in a Go routine, you're just listening on the connection that you have with the peer, right? And this is just an ordinary Go like net.con interface, which is actually a TLS connection because we did the TLS handshake, right? So you're just being like, read, right? Read from this connection. Read what the peer is sending me. And then similarly, there's a Go routine where you're writing messages, right? You just say like, you know, I, the network layer, have been told by the consensus engine or wherever else, I have been told to send this peer this message, so here's where I do it, right? Like I am told to write this message to node ID such and such, and inside of this Go routine, here's where I actually do the write on the network, right? This is where I do like write on the net.con. So what happens if the peer just like becomes unresponsive, right? So like maybe their Avalanche Go process dies and then you just never hear back from them. So we put a timeout on reads and writes so that if that occurs and you are unable to finish a write or a read in a certain timeout window, then you're just like, okay, whatever, close this connection, I'm done with them. And then maybe you'll try to connect later, but for now you're just like, I can't talk to this person, so I give up. And then we also periodically send keep alive messages, basically, or we call them ping pongs, to ensure that we stay connected even if there's nothing to say. So like every so many seconds, I'll send you a ping message and be like, hey, I'm still here, don't time out on me, I'm still alive. And then you respond with a pong message, which is, we've actually changed the pong message to include some information. We've actually changed it to include what you think the peer's validator uptime is, right? Because we're gonna send these pong messages anyway as part of the keep alive. So we were like, well, we might as well include some useful information in there, right? So if I'm talking to you and you're a validator, I'll also include in that message, just kind of like writing along for free, so to speak, what I think your uptime is. So if I think that your uptime is like 95% and you're like, ping, I'm still alive, I'm like, pong, okay, got it, you're still alive. By the way, I think your uptime is 95%. And the reason that we do this is it's a useful metric for you to have as a node operator, to be like, well, I'm getting a lot of pongs that say my uptime is like 70%, right? So something's not right here. And this lets you get like an assessment of what the network thinks your uptime is. And if you have like the Grafana dashboards that we distribute, like this is how we populate the panels about like what the network thinks your uptime is. So the way that we actually pack messages to be sent over the wire is we always send a uint32 that has the length of the message that we are about to send, and then the actual message itself, right? So a little bit more specifically than what I was saying before, the go routine is doing while we're still talking, right? While we're both still connected and alive. I read the message length, right? So you send me like 16 or whatever, and I'm like, okay, cool. The next message that I read from you, I'm gonna read the next 16 bytes, and then once I've read 16 bytes, I'm gonna try to parse that as a Avalanche Go message type. And you know, if I can't parse that, you told me it was gonna be 16 bytes, and I tried to parse those 16 bytes, and I couldn't do it, so something's wrong, right? Couldn't parse your message, just ignore. Okay, and similar on the other hand with writing. Okay, I realize that I'm a little short on time, so I'm gonna kind of breeze through a few of the next things, and I don't mind staying a little bit after for questions. I don't know if there's someone in here after me. So the consensus engine has this interface that it uses to send stuff, right? And the interface that it uses is this networking library that we're talking about, right? So the consensus engine doesn't really care about the implementation details of the stuff that we're talking about. The consensus engine is just like, I want to send this message to this node ID, go do that. And this is the abstraction that we provide to the consensus engine so that it can do that, right? The consensus engine doesn't care about like, oh, you're doing your handshake, you're doing this, you're doing that. It's just like, send this message, right? So we have this network struct that handles a bunch of kind of the metadata and like management of all these peers that you're connected to, right? So it's like, you know, who are the peers that I'm connected to? Who are the peers that I'm connecting to? All of that is inside of here. And that implements the interface that I was just talking about that the consensus engine has access to. You might be wondering, how do you like get connected to anybody in the first place? Well, in the code, there's a bunch of node IDs that are listed and IP addresses, and you just randomly sample some of those, and you're like, okay, well, I'm gonna just ask these guys who else I should connect to, right? So you initiate some connection with them, and then they tell you about people, and then you connect to them, and then they tell you about people, and so on until you're well connected. You can use whatever bootstrap or beacons you want to bootstrap from. It doesn't have to be the ones that are predefined and randomly sampled. I'm gonna have to kind of gloss over all this because I've got like a minute left. But there's a bunch of different messages that you could send back and forth over the network. Here's the ones that are purely concerned with the networking layer, which is the stuff that we're talking about here, right? So there's the version message that I mentioned before, the peer list, the ping pongs. There's some message types that are specific to bootstrapping, right? Like getting up to speed on like what the tip of the chain is and what's happened until this point in time, like getting the chain history. And then there's a bunch of consensus message types, right? So this is the stuff that's concerned with like actual Avalanche consensus, right? So, you know, a pull query, for example, is like, hey, what's your preferred frontier? And this preferred frontier is like an Avalanche consensus term. It basically thinks like, what do you want to see be like the next block that gets accepted? And then chits, for example, is the response to a query. Someone asks you like, what do you think should be the next accepted block if you had it your way, so to speak? And you respond with chits, which is basically, you know, here's what I think it should be. Okay, and then we also let VMs send arbitrary messages to each other, right? So like we can't enumerate all of the different kinds of messages that an application will want to send between different instances of it. So we just have these kind of generic app messages, and there's a certain semantics and guarantees that the VM has that if it sends an app request, eventually it gets a response, and so on. Networks are unreliable, so we register timeouts, and if we don't get a response in time, or if we're not able to send a query at all, we just time out until the consensus engine like couldn't send that, sorry, right? Consensus engine says, send a query to node ID A, we're not connected to node ID A, consensus engine is immediately informed, sorry, couldn't send that. And then it's the consensus engine's problem to deal with it. And these two slides are just about like how we actually implement those timeouts and deal with unexpected messages. I'm just going to kind of gloss over all of this as well since I'm 2 minutes over, but we do a bunch of rate limiting to make sure that you don't accidentally get DOSed or on purpose get DOSed.
Question, how do you do with the, it's a security concern because you're exposing your IP address and your port to probably a machine that is, might not be the case, but it could contain the private key too. How do you protect yourself? Because everyone gets broadcasted, not broadcast, but it's your IP address and your port is sent to a bunch of people that are connected to the network.
Yeah, I mean, you just should follow the best practices about, you know, don't let anyone access any ports on your machine that they don't absolutely need access to, right? So if you're running a node, you should only have the P2P port, which is by default 9651, open to the world. And, you know, there's only so much that you could do past a certain level, right? Like in order to run certain applications, you have to have a port open to the world, and it's just on you to make sure that you're following best practices and not like overexposing yourself by like leaving port 22 open and like letting people try to SSH into your node and stuff like that. And you know, unless there's some horrible flaw in our code, you know, they shouldn't be able to like extract your private key just by being able to like connect to an Avalanche Go node running on this port. But you know, you always got to be concerned about security when you have like, you know, random people on the internet connecting to your machine.
You mentioned that Avalanche Go validators have to connect to all validators, and that the network can scale to, you know, 1 million nodes. Are there any software limitations when it comes to open file limits, et cetera?
Yeah, so I think the number of connections that a Go program can handle is significantly larger than what exists now, right? Like I think that there's example programs out there that handle like tens of thousands at least of TCP connections, maybe even hundreds of thousands. But like, yeah, you do start to run into some of these limits. I think Stephen actually is a good person to ask about because we have thought of this before, and there might be ways to like rejigger the like how Avalanche Go works so that you don't need to be connected to to all of the validators at once, which, I mean, not super worried imminently about the validator set blowing up so large that like you run out of file descriptors or like, you know, even, you know, really good hardware can't like keep all those connections alive. But it is definitely a valid question, and I don't know. There's probably ways that you could mitigate that and get around it.
Just a quick question about timestamps. You said in the message for handshake there's a timestamp included. How do you obtain this? Is it a Unix timestamp? Do all nodes need to be in the same time zone, or?
Yeah, so I apologize. I think it might have been a little bit more clear if I were able to pull up the code. So in the version message that I send to you, I say, this is, you know, here's my IP address. Here's my certificate. You know that because we did the handshake. Here is what I think the time is, right? So it's just what I think, like my local Unix time, right? Like time.now and go. And then I include a signature over the IP address and the timestamp, right? So that if anybody else wants to, right? So now let's say that you tell someone else about me, right? You're like, here's our IP address, here's what they think the time is, and here's their signature. So now they might be a little suspicious. They might be like, I don't believe you that that I said that my time was such and such, right? But they can use signature verification to actually check that I was the person that created this message. I am the person that said my timestamp is T. And the reason that we want to have that is so that that person can know like what was the latest IP address that I broadcast, basically. So they can verify that I am the person who broadcast my latest IP address. I know that was a little bit involved, so. All right, well, thank you all so much. And I'm happy to take any more questions if you got them down here.